Okay, welcome back. My name's John Myers, and website's pixelsite.org, and we've got the YouTube channel as well. So as you can see, we got a bunch of stuff laid out here, and we're going to walk through this stuff. This is going to be a three-part video, and we're going to talk about telescope optics, telescopes, and this guy here, the Star Adventurer. The main thing is to throw it all together and make some sense out of it, and try to put it together in a way that's a little bit more understandable for somebody that's interested in astrophotography, telescope optics, and that kind of thing. What I wanted to do was create a video that kind of walks through a lot of the stuff that I had to learn when I got into astrophotography. It took me weeks, months, years to gather all this information to where I was ready to actually go out and deep dive into the hobby. So what I wanted to do was walk through the basic equipment. I'm going to start out with telescopes, different types of telescopes. We're going to talk about accessories. We're going to talk about mounts. And we're going to get into optics, and we're going to get into DSLR equipment and things like that. But in order to kind of walk through that in a reasonable way, we want to break it up a little bit. So the first video that we're going to do is going to talk primarily about telescopes, different types of telescopes, different optics, because it's really important to understand the optics when you go out to buy a telescope. We'll talk a little bit about F numbers and things like that, glass and all that kind of thing. And I want to make sure you understand that before we get into the telescopes and start walking through the telescope. Some of the videos are a little bit boring. It might be a little bit long, whatever the case is, so you can kind of like jump around if you want. We have some really nice equipment laid out here. So we have a Celestron Edge HD 9 1/4. This is a Schmidt-Cassegrain, or also known as a catadioptric type of telescope. It is a reflector telescope. I do not have a Newtonian reflector, but I'll show you some pictures of those. They're common, and a lot of people use them for astrophotography. We've got three different refractors here. We have a achromatic doublet right here. So this is a basic 1000 millimeter refractor. We actually have a much larger diameter triplet APO. This is a Skywatcher Esprit 120 ED. It's got ED glass in it, and it is a triplet APO, and it's outfitted with a star guider and a guide camera. And then over on the desk here, which I don't know if you can see it, but this is a 71 millimeter William Optics triplet, and it's called a Gran Turismo 71. So you'll see different pictures of these and different comparisons of framing and so forth in the video. So we'll walk through all that, and you'll get an opportunity to see the optics of how these different scopes work. DSLR photography or astrophotography is a really good thing to try the hobby out the first time. You can use a number of different cameras. You can use a telephone, or you can use your cell phone. You can use the, you don't want to use a telephone, but anyway, you can use a cell phone. You can use a DSLR. You can also use small cameras like this if you have a little selection on there to get your settings for your exposure. These can be a lot of fun. The last thing I'll say before we get into it is do your research. There's a lot of stuff available out there. Understand the different optics. Make sure you get a sturdy mount no matter what telescope you buy. You got to have a sturdy mount for the base platform for astrophotography. The reason why is because those stars are real small, and any jiggle at all will give you star trails. So anyway, that's it. Let's go ahead and get started, and hang in there. Again, some's boring, some's kind of cool. I'll try to throw up a whole bunch of pictures while I'm doing it, and we'll see how it works. All right, so we've got the small guys here. This is a 60 millimeter Meade refractor, made in China, and you can kind of see there that it is pretty wobbly. I would try to stay away from anything that's super flimsy. Stay away from the flimsy ones, and you're not going to be able to steady this thing a whole lot. And so, I'll call it a kid's scope. It's definitely nice for an introduction scope. Get your kids to go out and take a look at the moon. It's kind of cool. You can take it down and put it on your balcony. It's good for looking at the moon. It's awesome for looking at the moon. Give it to your kids. So if you want, you can take it out on your balcony and look at the birds, look at the airplanes, like birds, the moon, maybe some ships or whatever in the ocean. These are nice for kids. And lightweight. It's just not stable. I don't want to spend a whole lot of time on it. This is, like I said, this is a kid scope. I would just take it out of the selection. We'll set that one aside. We'll move up to this guy. All right, so I wanted to get that out of the way. Obviously, when you go out to buy a telescope, you don't want to buy a child's telescope to do astrophotography. You can certainly try it. Your kids can try it. You could probably take some pictures of the moon or something like I was showing you, but they're really not made for astrophotography. If you want to move up to astrophotography, there's a number of things that you need to understand about the scope. How the optics work, the difference in the way that the light's reflected in the tube, and then what kind of glass are the lenses made of, what is the basic optical design of the telescope. I'm not going to go real into depth into all of the different things about telescope optics, but there are some really important things to understand if you're going to go out and buy a telescope, or if you want to do astrophotography. So basically what we're going to talk about is the light gathering capability of the scope, the F number of this scope, and the focal length of the scope, and how these interchange in calculations to determine your F ratio, the power and the magnification of the scope, and that kind of thing. So basically we have three main types of scopes. You have a refractor, where you have no mirror. It's all done with basically glass lenses. You have the reflector, which has a giant mirror back here, and in a Newtonian it's the same. And what happens is the light comes through the front of the telescope and it goes back and it bounces off that primary mirror. This is where things start to change. So in a Newtonian reflector, basically the light comes back and then hits a mirror and gets directed right up to the eyepiece. So you have the focal length, which is the distance back to the mirror, and then where it's reflected and goes up to the eyepiece. So that's the focal length in a typical Newtonian reflector. Now if you get a catadioptric design, you have an extra bounce of the light path. And so what happens is the light comes through the main objective, hits the mirror, comes up and hits a secondary mirror, and then gets bounced back all the way to the back of the telescope through the center, right through the center of the mirror to the eyepiece. There's a hole in the middle of the mirror, and that light path goes right through it. So what that does is it increases the light, or the focal length, the distance that light's traveling within the telescope tube. It increases that tremendously, and so you'll have a telescope that's short like this. It appears short, but it's that light bouncing back and forth inside that gives you that long focal length. This scope right here is 2,350 millimeters. This one's only 1,000 millimeters. Again, the light comes through the refractor and basically it converges to a point right in front of the eyepiece, and that's basically the light path. The distance from the objective up to that point where it comes together is called the focal length of the scope. Now with a scope like this, you have a much longer focal length because your light image is coming into the scope, it's bouncing off the primary mirror, then it's coming forward to a secondary mirror, and then it's bouncing off that and going back. So all of that creates the focal length of this scope. This scope, the native focal length is 2,350 millimeters. In this scope, it's only 1,000. It's just one shot straight back to the eyepiece. Now, that focal length also calculates directly into the useful magnification of the scope. So I'll show you those formulas, and I'll put them up on the screen, either over there, probably. When you're working with a really powerful telescope, or a telescope at high power, it becomes really, all the other components become critical, and especially your mount. So this is a longer focal length. We have another type of reflector. If you look down here on the screen, it's called a Newtonian reflector, and that's a common big light bucket Newtonian reflector. They also come in, there's a term called Dobsonian. Dobsonian telescopes, basically, they're the type of telescopes that you go out and you have a platform, and basically the scope rotates on the platform and you can swing it around and look at it for pretty much for visual observation, not for astrophotography. Newtonian reflectors, on the other hand, would have typically a German equatorial mount, and you can set those up for astrophotography. So 3 types of scopes. One, the little skinny guys, that's a refractor. You've got the short, fat ones, that's a Schmidt, catadioptric Newtonian. And then you have a regular Newtonian, which is pretty much a long tube, and you'll see those on a German equatorial mount like this. Each one has pros and cons. The refractors basically, because of the way that the light comes through here and the lenses that are used in these, you'll hear the term achromatic and triplet, doublet, that type of thing. Achromatic and triplet, doublet, that type of thing. And basically it has to do with how the light is focused. So the lower end scopes are typically of a doublet design, and the doublet has objectives made of flint and crown glass up here. Now, one of the things that you want to look for in a telescope, if you're concerned about clarity and design, be careful about chromatic aberration. Different telescopes, especially some that are on the lower of the line, the glass elements are made of crown glass and flint glass, normally sandwiched together, and that's an achromatic design where you just have the 2 lenses. In some of the really cheap telescopes, and generally achromatics, basically what's occurring is when that light comes back, there's 3 channels of light that are coming through the telescope. It's a red, a green, and a blue. And in the achromat, it comes back, and those color channels focus at different points. So the red and the blue focus, I believe they focus just after where the green focuses. And so what happens, because you have different focal points for the different colors, is you'll get a halo around the object, like the moon or whatever the case is. But it's noticeable, and stars seem to be more expanded or a little bit larger than they really are. But when you move up to a triplet design, which is like the ones I have here on the table, this glass element is a stack up of 3 different types of glasses. And basically what that does is it corrects that light path so that the colors come to a focus there in front of the eyepiece at the same point. That really increases the clarity of the star. You get pinpoint stars, and that's a triplet design. So you have achromats that are basically doublets, and then you have triplets, which are apochromatic telescopes. So apochromatic, achromatic, doublets, triplets. Achromatic and triplet, doublet, that type of thing. When you move up above this line, you get into what's called a triplet. And the triplet APOs, or apochromatic refractors, are probably the best for astrophotography that you can really get. And the way they work is they have a different stack up. There's actually 3 elements of glass. You have the crown glass, and I think that they'll use a glass called fluorite, some of the older ones. They've changed to what they call extra low dispersion glass, which is ED glass, because fluorite had issues with being brittle and so forth. But anyway, it depends on the manufacturer and their process on how they make that glass. But essentially there's 3 layers, and what that does is it causes that light path and all those channels in the light path to converge at the same point, so that you don't have halos because there's a different color that's focusing at a different point. Again, it's a triplet design, or apochromatic, converges all light colors at the same time and gives you a really nice crisp image, so you don't have halos around the moon or planets and things like that. Sometimes if you look with like that little the small telescope that I showed you, if you're looking at Saturn or Jupiter or even some of the stars, you'll see kind of a halo just around the perimeter of the moon. It'll be like a blue band, basically. That's called chromatic aberration. And chromatic aberration is caused because those colors are not focusing at the same point. So anyway, in terms of the optics of these telescopes, if you in the achromatic and triplet, or doublet and triplet design, these are excellent scopes. Top of the line astrophotographers typically use the APO, and we'll show you one of those. I've got one over here on the desk. It's a Skywatcher 120 ED. It's a really nice scope. It's my primary scope that I use for astrophotography. But anyway, it just depends on what you can afford and you know, what you're willing to go out and experiment with. But that's the basic optics inside the refractor. The art to astrophotography is time exposed photography, basically, where you're capturing that light over an extended period of time, and that's what's giving you that picture. One of the main things that you really want to look for in a telescope is its light gathering power. So if you notice, this is a really thin telescope. That's a really fat telescope, and Newtonian reflectors are really big, light buckets they call them. And so you'll see the term f-stop or f number on the scope. Basically what they're talking about is the f number, just like it is in camera lenses. It's the ability of that lens to bring in the light. So the aperture, literally the diameter in a camera lens, actually changes depending on the setting that you have, and I'll show you some pictures. But basically there's an opening that light can travel through in your camera lens, and the lower the f number, the bigger around that aperture is, the faster, quote, faster it is, because it can gather more light quicker, because it's a larger opening. So that's all that f number really means. And so if you have a low f number, you have a larger aperture and you can get that light quicker, which is really important for astrophotography. You're trying to gather as much light as possible to prevent the issues that you might have with tracking, with noise in your photos. You know, if you have to take a longer picture to capture that light, you're going to get a lot more noise in the image that you're going to have to process out later. So keep that in mind. The f number is important. And it's kind of a trade-off when you go to a telescope to buy one. You'll look at the f number and you say, well, I want a low f number, but I want a lot of power, and so you have to balance that out. For beginners, you don't really need to worry a whole lot about that stuff. You can do it with trial and error, and just go out there and give it a try and see what happens. There's nothing wrong with that at all. But if you really want to do some serious scope shopping in the beginning and get set up right away, and you haven't gone through that stuff yet, be careful about your f number. Take a look at your f number. Look at the glass type as well. So are you, and the telescope optical design, is it an achromat? Is it an apochromat? Because there are some pretty substantial differences for astrophotography with those designs. Another thing you want to look at is you want to look at the type of glass that's used. There's a glass called extra low dispersion glass. It's ED. You'll see that term. You may see FPL53 glass. What that has to do with is the ability of that glass to actually do a similar thing that the apochromat does, which is to normalize those channels as they come back to a focus point, to make sure that the channels arrive together at the same point in front of the eyepiece. So that's really important. These scopes are not as good as gathering light, so they are a higher f number. This is an f11. This has a long focal length, like I said, so it's also a high f number. This is an f10 because it's got a longer focal length on it. But if you look at a Newtonian reflector, you're talking about like f5 or f4, so they're just gathering a lot of light. But with a Newtonian reflector, you get really good, sharp images, but not quite as good as what you can get with one of these, with a good refractor or a top-of-the-line Schmidt Cassegrain like this. Now people will argue that I actually don't own a Newtonian. I built one. I built a Newtonian reflector years ago out of a Cobra helicopter tow missile launcher tube. Cobra helicopter tow missile launcher tube. And we found one in the DRMO, where they take all the scrap stuff that the Army had in Germany. And lo and behold, we found a tow missile launcher. And I took and ground the mirror for that using different carbides and oxides and things like that. You grind it on a table. It takes about 20 hours to do that. And then you go through the whole process of testing the mirror and figuring out, grinding it to the right focal length, and then polishing into a parabola and all that. And I did that, but the scope worked okay. It certainly wasn't anything that I could use a lot and enjoy, but it was a fun accomplishment. So that was the end of that. And then I bought a catadioptric It's basically a reflector telescope, just like a Newtonian, but it's enclosed. And that was from a company called Bresser, and I wasn't too impressed by that scope. And then I got rid of it, and I bought the refractor. So I don't own a reflector, but they are good scopes. There's plenty of guys out there that are using them. It's just all depends on the combination of optics and budget and all that stuff that that the individual basically will make a decision on. So anyway, that's it with the catted dioptric. These are what these are really good for is if you really want to zoom into things like galaxies that are really out there, far out there. If you have certain features of nebula, like if you want to zoom into the middle of the pillars of creation, this is an excellent scope to do that with. But 9 times out of 10, what you're going to be looking at, all the common things, Andromeda and the Eagle Nebula and then some of these larger nebula, they will not fit into the field of view of this telescope. They're going to be that big compared to what you're going to see, or compared to what you're going to be able to frame with a camera on this guy. So again, you have refractors, Schmitz, Newtonians, Dobsonians, and I'll show you the pictures on the screen and give you some of those formulas so you can look at some of what I'm talking about. With a scope like this, one of the things that you really need to think about is what are you going to take a picture of? What do you want to shoot? Because there's a huge difference. And I say this to a lot of people, and it's probably one of the another key thing about astrophotography is people don't know how big deep sky objects are. And so I can aim at the moon with this telescope right here, and I may see the moon. It may fill most of the frame. We'll call it the frame. We'll pretend we're shooting through a camera. But I'll see a certain amount of that moon in the eyepiece or the frame of the camera through a telescope like this, right? Well, if I aim this up to an Andromeda, which is a galaxy, it's 2.5 million light years away, and I look at that galaxy is actually larger than the moon, and it may not even fit in the field of view of the telescope. So you have to be really careful about getting too excited about buying a big telescope like this, or even one like this. Now, this guy here, and I'll see if I can pick it up without too much of a disaster. This guy right here is a Skywatcher ED 120, so it's 120 millimeters, and that's a large scope. And believe it or not, with that scope at the native focal length, I can't fit Andromeda into the frame. It's only 840 millimeters. Now, if you remember, I said this was 1,000 millimeters. It's less aperture, smaller, so it doesn't gather as much light as a big APO like that. But in terms of power, if I connected an astronomy camera to this, I would see less of Andromeda with this scope than I would, with a small scope. In other words, when I say I see less, I'm too zoomed into Andromeda to see the whole thing. I want to see less of Andromeda because I want to zoom out, and so I would need a telescope ideally around 71 to 80 millimeters to capture all of Andromeda. The galaxy is actually that big. So when you go to select a scope, don't be worried about the size of the scope. Be worried about the quality of the scope, quality of the mount, quality of the optics, and spend the money there. Don't spend the money on a big scope, because if you go to a big scope like this, there's a lot of complexities that come to this that will make it frustrating in the beginning. So start out slow, learn the basics. There's a lot of astrophotography software and a lot of settings and everything that you have to do if you get into serious astrophotography to make something like this work. So start slow, start with a basic mount if you can get a basic mount. But if you want to go ahead and jump up, spend the money on the mount. That's the first place you want to put your investment. So if there's a questionable decision on whether or not you want to buy an APO or an apochromat, and you have a set budget, and then you're making it, you're looking at the mount, and the mounts, one mount's a little more expensive, but it's a better mount, maybe, from reviews or something, you find out that's a better mount, then, go with the better mount. because you may find that the optics in the telescope aren't going to matter as much as the tracking accuracy of your mount. So be really careful there and do the research, look it up online, and just be sure that when you make that decision for serious astrophotography that your mount's sturdy. When you do make a decision on a scope, like I said, be careful of the field of view. There's a really nice program. It's called Astronomy Tools Field of View Calculator, and it's online. You can go online and you can enter your camera equipment, your focal length, your diameter, your sensor size, and then select the object from the drop down. And what it'll do is it'll overlay your frame and what that object's going to look like in your field of view. And that's probably the best tool out there on the internet to look at what you're going to get for the telescope that you're interested in. So make sure you go on there. Again, it's Astronomy Tools Field of View Calculator, and if you Google it, you can find it. And there's a whole list of all the known telescopes that are out there, and astronomy cameras as well. So each combination. Another thing that I'll mention really quick is that if you buy astronomy cameras, the astronomy cameras have different size sensors in them, and depending on the size of the sensor, your field of view will change. So I may have this astronomy camera, which is an ASI 1600, this little red guy in the very back here, or I may have this one, which is an ASI 2600. But from the outside, you really don't see the difference. They just look like round cameras. But inside, there's a lot of difference, and it's in the sensor. And the sensor on that actually gives me a much larger field of view than the ASI 1600. And then when I put, if I use this camera on this scope, I can look at larger things because I can fit it into the field of view. But when I use that camera on a big, powerful scope at a long focal length, my field of view really shrinks. And the only reason I have this one on this telescope right now is because I was zoomed all the way into the pillars of creation, which are really, really small, in the middle of the Eagle Nebula, which is really, really big. So that's what this was set up for. So be careful about the telescope combination, focal length, and the camera that you're using. And if you use that tool online, the Astronomy Tools Calculator, make sure that you look at the camera that you're thinking about buying, or at least try a couple of different cameras out and look at the drastic difference in the field of view just based on the change to the camera. And you can leave the telescope alone, but that sensor has a lot to do with the magnification of the field of view. Now, another thing while I'm talking about the astronomy cameras really quick, so you have monochrome, which is on this, and you have full color, which I have on this one. Depending on where you're at and the type of imaging you do, you may want to do broadband imaging, which is full color. And I say broadband just meaning full color. If you want to shoot nebula and things like that, a lot of times astrophotographers will use different grades of filter, and we'll talk about that in the accessories. But as you shop for a scope or an astronomy camera, actually, you're going to want to make sure that you understand why you might want a monochrome camera instead of a full color camera. And that way, because that's going to take you down a whole different path in terms of costs, but also the dedicated light capture of a monochrome camera that you could put through a filter, and the way that the sensors are designed for doing that. Basically, in a monochrome camera, 100% of the pixels in the sensor are designed in a way to just capture all that light. In a full color camera, they're designed to basically divide up that light, and there's different sets of those pixels that receive red, green, and blue, but they don't all collect the same color. So you have maybe a third of the sensor actually collecting the overall image. It's just compiling that color into a single image. Whereas if I shoot through the monochrome camera and bring all that light through, all the light's going to come through, and it's going to create a single frame, but I have to do it 3 times to get all 3 colors. So it triples the amount of time that I have to spend out there taking pictures. So that's a really important thing. Basically you have to take 3, 4, 5 times the number of frames to get a full color image with a monochrome camera than what you would do with a full color camera. So that's important. All right, so that's it. I think I've talked enough now. Hopefully I can cut this in somewhere and have it fit in and make sense. But I want to go through that before I press on to the German equatorial mount. Okay, so that's the end of that part. I hope that was useful. Anyway, that we talked about little telescopes, we talked about the medium telescope, we talked about the Schmidt-Cassegrain telescope, and I hope that helped a little bit with selection of telescopes. But there are some really important things to look for. You know, what's the light gathering power, you know, of the telescope that you're looking at? You know, how good are the optics? What can you expect to see through the telescope that you choose? You know, what's the frame that you're going to be able to get if you attach a camera on the back of that guy? You know, don't get a telescope that's too big until you're ready. Remember, there's doublets, there's triplets. They focus light differently. You know, the triplets focus the image, all three colors are right there at the same point. Doublets, there's a slight offset and you get that halo, and you're more likely to get that chromatic aberration. So keep that in mind. The mounts, you know, lots of differences in the mounts, you know. So for a scope that maybe isn't so expensive but perfectly capable of doing astrophotography, you'll get a German equatorial mount typically with some kind of a drive unit in it. If you're you know, driving around town and you know, you look it over at somebody's lawn and they got a garage sale going and you see a telescope like this, go ahead and stop, you know, check it out. Maybe it's got a German equatorial mount. And maybe you can do what I did and, you know, adapt a DSLR camera on there, or maybe you can slap a camera on the back of the telescope. So always keep your eyes out. You don't have to necessarily go out and buy new stuff. You can do some really cool stuff, which is old equipment. So that's important. Make sure your stuff's sturdy, you know. Like this Star Adventure, I went ahead and slapped it on a good tripod. The tripod's really important when you're actually, you know, for a platform to do photography or astrophotography through. You want to make sure that you have a nice solid mount, so keep that in mind. Try to make sure you can level it also on the ground if you're tracking. Yeah, so that's it. Mounts, telescope, glass. ED glass is cool. It's real crystal clear. That ED glass kind of works the same way as a triplet. It's just another way to get that light to focus all channels at the same point. So that's what the ED glass basically does. They used to use fluorite for that, so we talked about that. I showed you a bunch of pictures. Little scopes take excellent pictures of big nebula. A lot of nebula are really big. They fit perfectly and frame nicely in a you know, in a scope like that. The larger refractors, this, you know, the 120 millimeter here, it's a perfect in between like deep sky, powerful, and also, you know, on the smaller end of the deep sky objects where you could still capture enough in your frame to make a really cool picture. If you have the option, a good transition is probably 60 to 70 millimeter, jumping up to like 120 to I think 120 is a really good number, actually, to be honest with you. Once you get up into 140 and 150, you start really making a decision on whether you want to invest in that. You know, they're extremely expensive, and you can get a Schmidt-Cassegrain and do about the same in terms of the magnification and the framing and stuff like that. So anyway, the bottom line is do your research on the telescopes. I hope all that helped you. Again, my name's John Myers. The website pixelsite.org and the YouTube channel is Pixelsite. I hope you like the videos. Go take a look at the other ones if you have the time. I've got that one I just finished on the Eagle Nebula. That's pretty cool. And that's it. So there you go. Clear skies, and I wish you the best.